Welcome to the lesson on simple harmonic motion. In this lesson, we'll be discussing simple harmonic motion and analyzing the values of displacement, velocity, force, and acceleration at 4 key points during the simple harmonic motion. And we'll also be discussing the period formulas for the pendulum and for a mass oscillating on a spring in simple harmonic motion. Let's get started by looking at simple harmonic motion and being able to recognize simple harmonic motion and identify the values of displacement, velocity, acceleration, and force at different points in the motion. This is a little tricky. So to start off with, we're going to take a look at this animation, talk about simple harmonic motion, and talk about those 4 key spots. All right, here we are in an animation that we showed earlier when talking about spring force, and elastic potential energy. This time we're going to use the spring to demonstrate simple harmonic motion and the key spots that we're going to analyze here in a moment with regards to displacement, velocity, acceleration, and force. And you notice that I've set our spring to have no friction. If there was friction, it wouldn't stay in simple harmonic motion. So this is an ideal frictionless environment. I took a 100-gram mass and I hung it from the spring and got it to stay at rest. And you can see that at rest, it's at about the 40 centimeter mark. This is key because this will become the equilibrium position during oscillation. It's the spot by which the motion will take place back and forth. Now to prove that to you, if I take and I raise the spring with a mass attached up to the 20 centimeter mark and let go of it, if the 40 centimeter mark is truly the equilibrium position, then where should the mass and spring bottom out and change direction? Well, it would make logical sense that I just raised the mass 20 centimeters. If 40 centimeters is the equilibrium position, then this should bottom out at 60 centimeters. Let's take a look, let go of it, and take a look here. That's pretty fast for you to see, but you can see it's bottoming out towards the bottom of the little ruler here that's on the screen. But if we slow this thing down to quarter time, you can see the oscillation a little bit better. And indeed, it's oscillating back and forth with the 40 centimeter mark as the equilibrium position, with 20 centimeters above and 20 centimeters below that spot. Okay? And you can see it just keeps going back and forth, back and forth. This is simple harmonic motion. It's repeated. But what makes this more than just periodic motion is the fact that the values of displacement, velocity, acceleration, and force can all be analyzed and go in a cyclic manner. Okay? If I'm going to slow this down just a little bit more, the key spots that we're going to be taking a look at here are the equilibrium position itself, which we're going to call spot A, is when the mass is on its way back down. Spot B will be where it bottoms out. Spot C will be the equilibrium position on the way back up. And spot D will be the top of the motion before it changes direction and heads back down again. Okay, you're going to see this labeled in a diagram here, and I greatly encourage you to add that diagram to your notes as it will aid in understanding. But here we go with simple harmonic motion slowed down at 1/16th speed so you can see the values as they're going up and down here. And we're going to take a look at these in more detail here in chart form in a second. All right, so what you can see here on the left, we have a still picture of our mass in simple harmonic motion just viewed. And we have this chart set up over here. And I would greatly encourage you to pause the video and set this chart up. And what we're going to analyze is the displacement, velocity, acceleration, and force at each of the key spots mentioned previously, A, B, C, D, and then back to A. Again, A is the equilibrium position when the mass is on its way down. B is the bottom of the oscillation. C is the equilibrium position on the way back up. And D is the top of the oscillation. All right, so go ahead and get this chart ready to go. And what we're going to do is identify the values where the displacement, velocity, acceleration, and force are at their zero values, at their positive max values, and at their negative max values. So take a moment and get that set up and we're ready to go. Okay, here we go. So at point A, what is the value of the displacement at point A? Now remember that x is the stretch or compression, in this particular case, beyond the equilibrium position. We established previously that the 40 centimeter mark is the equilibrium position. So at spot A, x has zero value. Okay? So 0 would be the displacement at point A. At B, which is at the bottom of the oscillation, we would say that B has reached its negative max value. The reason, of course, is from the equilibrium down traditionally is considered negative. So this would be the negative max value for the displacement during the simple harmonic motion. Back up to point C. Point C has returned to the equilibrium position, so the displacement is again 0. Then we have at D is at the top of the oscillation, and here is where it's reached its positive max value. Then it returns to A again, where it is once again 0. Okay, now while we do each of these, we're also going to construct a graph of variable, in this case displacement, versus position during the oscillation itself. And we're calling it A, B, C, and D, but you could also call it 0, and then you could express B, C, and D in terms of angle, 90 degrees, 180, 270, and back to 0, for example, or pi over 2, pi, 3/4 pi, and then pi radians if you wanted to talk in radians. We're just going to do it as a function of position A, B, C, D, and A. If we go ahead and plot the points as we've demonstrated in our chart here, point A, the displacement at A would be 0. At B would be a negative max value. At C, back to 0. At D, a positive max value, and A, back to 0. Okay? Connect our points with a nice smooth curve. Okay? And you have the graph of displacement as a function of position during the key points in simple harmonic motion. All right, let's go back up now and discuss velocity. If you go back and recall the spring and mass oscillating that we viewed a little bit moment ago, as it's going up and down, it makes sense to us that B it must be 0 and at D it must be at rest in order to change direction. Hopefully it also makes sense that we can be going no faster than at the equilibrium position. So our maximum velocities will take place at equilibrium. For A, that value for velocity will be a negative max value. And the reason it's a negative max value is because the mass is on its way down, and down is the negative direction. As just discussed, at point B, the mass has to stop in order to change direction to go back up. So its velocity at point B is 0. At point C, it's again back to equilibrium, so we have a max value, but it's on its way up. So we would say at point C it has a positive max value. D, at the top of the oscillation, the system has to come to rest in order to change direction in order to go back down. So at D, we have a 0 velocity at point D. And then we are back to A, where we've already established that we have a negative max value at point A. Now graphing this, velocity as a function of position A, B, C, D, and back to A, okay, we have negative max value. And make sure you label them on your y-axis as negative max and positive max, and also the fact that the x-axis here is 0 velocity, and 0 displacement up here. Anyway, so negative max value at point A, 0 at point B, positive max value at point C, as in the chart above, point D back to 0 where it changes direction, and then back to A headed in the downward direction, so negative max value. Okay, connect with a nice smooth curve, and you have the graph of velocity versus a function of the 4 key points during simple harmonic motion. All right, now to continue the discussion, we need to analyze what's going on with acceleration and force. Honestly, the easiest way to sort this out in your head, because this can get confusing, is to remember that the force for an oscillating spring is equal to negative kx. I would encourage you to add that as a reminder up in the heading of your table. Now, if F equals negative kx, just think about it mathematically. X is your displacement over here. So, if F equals negative kx and x equals 0, then what is the force at that spot? It must also be 0. Okay? Now apply Newton's second law. F equals ma. If the force is 0, that means the acceleration also has to be 0. Let's now move to point B. At point B, we have a negative maximum displacement. Substituting that into negative kx, that would be negative k times negative maximum value. That gives us the maximum positive force at point B. Now, just a side note here. Another thing to help you with this is that remember, at point B, the force is trying to restore to equilibrium. So it's trying to bring the mass back up toward point A and C, which is the equilibrium position. If that's true, the force is acting upward, and upward is the positive direction. So the maximum force at point B, and it's directed upward, so positive maximum value. Now likewise, again, Newton's second law, F equals ma, then says that acceleration has to be directly proportional to and in the same direction as that force. So our acceleration also has a positive maximum value. At point C, we're back to equilibrium. No displacement, therefore no force, therefore no acceleration. At point D, where we have a positive maximum value for our displacement, up in our equation, negative k times positive max would be a negative maximum value for our force. Newton's second law follows that means the acceleration also has to be a negative max value. Back to this discussion on simple harmonic motion again, at D, the force is trying to restore the system toward equilibrium. And at D, toward equilibrium is down. So maximum force at D, also directed downward, so it has a negative maximum value. Back to point A, where we've already established 0 displacement, therefore 0 force, therefore 0 acceleration. Okay, now wrapping this all up, we'll finish with our graph of acceleration and force, and plotting our points and putting them on our graph. The acceleration and force as a function of the 4 key spots, A, B, C, D, and then back to A. Right from our graph, we have 0 positive max, 0 negative max, and back to 0. Connect them with a smooth curve, and you have, in this circumstance, the graph for the simple harmonic motion of the oscillation as described, and with all the 4 key points taken into consideration. If you have any questions on any of this, make sure you note and get ready to ask them in class tomorrow. All right, we're going to wrap this up with a discussion on the period formulas. The period formulas, especially if expected to be memorized, can be difficult, but I'm going to show you a little trick here that makes them easier to remember. Both period formulas, no matter if it's a pendulum or a mass oscillating on a spring, are T equals 2 pi square root and you have two quantities inside the square root, and they are in the form of a fraction. Here's how you remember this. 2 pi square root dependent variable over the constant. So t equals 2 pi square root dependent variable over constant. Now, let's apply this for the pendulum. The period for a pendulum would be 2 pi square root. What is the dependent variable? In other words, the factor that controls the period of a pendulum. You remember from previous discussion, reading, etc., that dependent variable is the length of the pendulum itself. What's the constant? What is the factor that remains constant for the period of a pendulum? And that constant, of course, is acceleration due to gravity. Now, be careful here. Acceleration due to gravity can change depending on location. Earth versus moon, for example, or further away from the Earth. But constant here because near the surface of a planet or a moon or whatever, it remains at a constant value. Okay? For a spring, same thing. 2 pi square root. What is the dependent variable that controls the period of an oscillating spring? And that dependent variable is the mass attached to the spring. What is the constant? This one's really easy to remember. For a spring, it would be the spring constant. And there you have it, the period formulas for both a pendulum and a mass oscillating on a spring. That'll do it for our lesson on simple harmonic motion. More to come as we investigate with problems in class. Ask any questions if you have any when we go over the follow-up tomorrow.